Okay, my name is Dick Belterman. I'm the coordinator of this web seminar series of the research seminar series. This is our last research seminar series of this season, but it's not the last seminar that Informatics Europe is doing. And I'll talk more about that at the end of this presentation. I'd like to spend 2 or 3 minutes talking about who Informatics Europe is, and then get on to introducing our speaker. Informatics Europe is a nonprofit, or I guess we should say a not-for-profit membership association, since profit is not one of our goals. The members of our organizations are mostly computer science departments or departments within institutes or research labs. The origin of Informatics Europe goes back 16 years now to the first European Computer Science Summit, which was held in Switzerland, where Informatics Europe is still located. And at that conference, it was decided that European computer science, the European academic computer science community, needed an organization that would protect the interests of research-based computer science across Europe, both in individual countries through our national members and at a European-wide policy level through the Informatics Europe organization. And in that way, we very much model the goals of the Computing Research Association in the United States, where we have close relationships with. And starting in 2006, so a year later, we set up an organization to represent the public and private research community of computer science in Europe. You know, it's Europe, so one of the first issues we have is a naming issue, and there we chose to call ourselves Informatics Research instead of Computer Science Research. Here's a map of our current members. Luckily, members are still joining us. We're nicely represented in the Nordic and in the Baltic countries. I noticed that Kaliningrad is colored in this map. That should be white because it's not a member state. We have large memberships across Northern Europe, in Germany and Holland, and in the Eastern countries, also in Central Europe. We have 2 members in Austria, and we'll be hearing from somebody from one of those members today, also in Spain and Portugal and Greece and Turkey as well. If you're from an institute or a department that would like to join Informatics Europe, our website has an indication or has a statement of how you can join it and what you need to be able to be a member. The kind of things that we do is to try and develop a common voice and common policies that help shape research and education in informatics across Europe. We also try to coordinate positions and act on shared priorities that support education and research, and also look at the social impact of the work that we do. And actually, the social impact is a very important area of Informatics Europe, where, and it's also a very important area where people need to look at stuff that's going on in our community. We try and foster knowledge transfer and collaboration across Europe by being a sort of meeting point, both across academia and also with our industrial members. And last but not least, the government and public institutions. Almost all of our activities are performed by scientist volunteers who donate their time, because all of us feel that this is an important venture that we can help bring people across Europe together. We have a number of different working areas in which people can participate. Those include, though on the list here, education and research, diversity, social impact, sustainability, data analysis and reporting, open science, and policy recommendation. And we also, through a number of academic leadership courses, a job platform, knowledge sharing, work on member empowerment, both our young members who are looking for career opportunities across Europe, and also our more senior members who are looking for other partners for things like European projects. One of the things we run each year is the European Computer Science Summit. This edition will be in Hamburg, in Germany, towards the end of October. The theme is a workforce for the digital transformation, and there are a number of sessions that'll be happening at that summit that I think are interesting and important for our members. One of the things that I think is important, and partially because I'm co-chair of this, is the early career researchers workshop in Madrid last year. There was a very popular place for young researchers. Because of COVID, many of them have not had the opportunity to present their work, have not had just the ability to go out and tell their story and to share that story with other people. And so following on a very successful workshop last year, we're going to host another one this year. The initial deadline for submitting abstracts is June 30th. But if you or if your students would like to have an event, Hamburg is an easy place to reach by train. And it's I urge you to take a look at the Informatics Europe website, look at the early career researchers workshop, and submit a note of intent for you or for some of your students. What we also have, in addition to this research webinar, is a gender equality in informatics webinar series. And that series will have its first edition next week. It's part of our European Network for Gender Balance in Informatics, and it's hosted by a number of important speakers. If you look at the website, then you can take a look at that. So that's starting next week, and I think that that's something you might want to register for. And finally, there's the Application Leadership Development course. Now, if you want to apply for this, you should do it tout de suite, because the deadline is today. It is a summer 2022 meeting, and that'll be held on location in Austria. There are a number of ways you can follow us. You can look at YouTube, where the older version, the previous versions of this webinar series are hosted. Follow us on Twitter, follow us on LinkedIn. But those of you who are already online now don't really need to follow us. You can just look at us right away and listen to the lecture that Laura Kovacs is going to give us. I'm very glad that Laura has been able to join us on this pre-summer afternoon. She's a full professor in computer science at the Technical University in Vienna. At the Technical University, she leads the automated programming reasoning group of the formal methods section. Formal methods is an area that is at the heart of computer science. It's at the heart of artificial intelligence. Many of us have touched this in our first courses in computer science, and some of us have continued to look at this in a time. Some people approach this area with some trepidation, right? Because they think, wow, this is pretty heavy formal stuff. But we're counting on Laura to guide us through in an easy to digest course with some meat in it for the diehards. Her other interests, or her interests, are automated search engine generation, symbolic summarization, computer algebra, and automatic theorem proving. Laura, thank you very much for joining us, and we look forward to your talk. And if you have questions from the audience, we'll monitor chat, and if we need to, we'll give Laura a shout during her talk, or I'll save them for the end. We'll see how it goes. Laura, you should be able to grab the screen.
Yep.
And we can hear you. We're all set to go. I'll go to mute. I suggest everybody else mutes themselves. I think everybody else has.
You can see the screen, the slide changing. Okay.
It's all fine. Thanks it's all yours.
Yeah. So yeah, thank you very much. It is actually summer in Vienna, so it's indeed early summer days. And so what I'm going to tell you, I try to be a bit high level, try to be a bit motivating on what is automated reasoning and how it helps automated program reasoning. I have some technical slides as well, and depending how time goes, I will see how much in depth I will go. So in a very vague sense, okay, so what's automated reasoning? As already Dick mentioned, it's really one of the foundations of artificial intelligence, but really think in terms of pretty much automated reasoning involves two main tasks. The first task, you're given a problem and you want to you represent this problem as a mathematical statement or a logical statement, a theorem, just like you know from math, Pythagoras theorem. That would be a mathematical statement. And the second step of, so once you have this formal characterization of the problem that you are tackling, the next task of automated reasoning is try to automate the reasoning about your problem. And by automation, I mean a computer-supported automated program checking the validity of your mathematical statement. And there are various nuances of automated reasoning, various applications of automated reasoning. It's actually a booming area. And in my group at the TU Wien, I'm actually tackling automated reasoning in the context of program analysis or software analysis, in particular to prove that software is correct. To some extent, the software is trustworthy, so at least meets mathematical requirements. We are also using automated reasoning techniques to generate program properties that, for instance, would prevent programmers to introduce errors while making changes in their code. You can use automated reasoning, and we are using it to synthesize programs from specifications, prove system security, and there are many other applications where automated reasoning can be used. But these are the main 4 applications that my group is working on. And the research that we are carrying out is funded by the European Research Council, by the Austrian FWF, Austrian Science Fund, the Vienna Science and Technology Fund. And actually, we do work with companies or research, these R&D sectors of companies, in particular with Amazon Web Services, Microsoft Research, and Certora. So let me just give you some things that you can do with automated reasoning for proving software correctness. And what I show you here, it's actually a screenshot of our own software program, which is called the Vampire software program, the Vampire Prover. It's about 200,000 lines of C++ code, so it's a medium-sized software. And this is what I show you here is a screenshot of a partial code of Vampire. So if I would now zoom a lot in this figure, you would see a lot of C++ code. So now just assume that it's a fictive code, so it's not anymore a Vampire, but assuming this big piece of code, there is this fictive or very small loop that operates some numeric variables, small a, b, and c, and also some capital variable a, which actually, and b, and capital C, which are used in order to represent arrays. I think, for instance, what can you do with your array? Well, you can actually represent segments in your memory. So now this program, it's artificial, it's small, but it's actually quite difficult to get it right or to get right its functional correctness. So what is functional correctness? So what is this program supposed to do? Or what, no matter how I execute this program, what kind of behavior this program should do? And this is an area where actually you can use automated reasoning. So you can have a computer program to reason about such computer programs or even bigger ones and generate so-called summaries or functional properties of this particular program. And such summary would be, and now I've write it down. So this is now things get complicated in terms of notation. But before I show you, let's just analyze a bit the semantics of this program. It does many things, but one particular interesting property is that if you start executing this loop, then you do a branching. So depending on the current value, the value of the current array element, if that element is positive, you copy it into array B, otherwise you copy it into array C. So one natural property, no matter how many times this loop is executed, one natural property is that every element in array B, it's coming from an element from an array element from A, because B is originated. Every element, every array position in B that is touched upon by this loop, it's coming from the array A. And now if you want to formulate this is where actually formal methods, or in principle, mathematical logic helps, because what you can say that every element, so you use a universal quantifier, that is every element in the array B, it's coming from an array A. You don't know which one, but you know that for every element, so for all positions in the array B, there is actually a position in A such that the two array elements correspond by equality. And with more, it's a positive element from A. So what I try to show with this very simple program is that just having like 5-6 lines of code can be actually very complicated. The size of the code doesn't give you the complexity. Depending what your code does, you can have very different kind of properties or functional properties of that code. And this would be one such property. But even in first order logic, you would need what we would say alternations of quantifiers. You have a universal property, universally quantified formula, and there is an existential quantifier inside. And with the work that we are developing in my group, we actually can generate such properties completely automatically in principle in no time. So we use automated reasoning techniques to come up automatically with such properties. Now, another thing which this program, that's what I didn't touch upon, is that this program is calling some function h. I didn't tell you what the semantic or what is the functional behavior of this function h is. But let's just assume a fictive call, and let's assume that this function h implements this kind of program, and the names are kind of intuitive. So it's a while loop that manipulates two variables, fib1 and fib2, and the names are intuitive. Actually, this loop is computing the Fibonacci number. So upon execution of this loop, we are going to get the numbers from the Fibonacci sequence, which is one of the most famous mathematical sequence. And this sequence with the property that the current value of a Fibonacci sequence is the sum of the two previous elements of the sequence. So it would be 0, 1, 1, 2, 3, 5, 8, 13, and so on. So I'm pretty sure that everyone who had discrete math, or even actually not even in university, but even in high school, or even before, heard about Fibonacci numbers. There are even children games manipulating Fibonacci numbers. So it's a very nice mathematical sequence. Yet, while we all know what Fibonacci numbers are, the question would be, okay, so what is the functional correctness of this program? What kind of properties this program has to fulfill, from which, for instance, we could ensure that the program indeed computes Fibonacci numbers? So while we all know what Fibonacci numbers are, an interesting question would be, okay, what is the relation? What is a relation between not 3 consecutive Fibonacci numbers, but just 2 consecutive Fibonacci numbers, Fibonacci number 1, and so fib1 and fib2 here in the program? And it's not that trivial to see, because actually the property that holds between 2 consecutive Fibonacci numbers is actually a polynomial property of degree 4. So it will be quite hard to come up with these properties in less than a second as a mathematician. But again, if you use automated reasoning approaches, in particular in computer algebra, we can generate you this kind of properties of the loop, again, in no time. So what you can do with automated reasoning, you can generate such kind of properties or such kind of properties. So either, let's say, with different logical complexity using quantifier alternations, or you can use a computer algebra polynomial arithmetic to express properties. And this would be very much in the flow of deductive program verification, where we are given a program, you're given a pre and post condition, you're given some contract of your program, and you want to ensure that your program meets its requirements. And for that, one would need to generate loop invariants and use this loop invariants to prove that the required contract is satisfied. So I might think, okay, so this is actually old school. Maybe it is, but it's quite challenging. But one fascinating area where automated reasoning is emerging, it's thanks to, or for us, for theoreticians, it's thanks, maybe for software engineers, is the burden of ensuring IT security, or ensuring security and privacy properties. And I claim actually, and also in our work, we claim that you can use very similar approaches that have been so far used for proving software correctness in terms of safety assertions. you can use the same approaches to ensure that your software is secure. So you can generate and prove security and privacy properties of your system. And let me just tell you, let me give you some, give you an example what you could do. So I give you a very abstracted challenge or application from security. So assume that, again, I have a loop in the software system. And in this loop, I take an input, an array A. And this array A is actually a bitwise representation of a secret key. And then I iterate over this array A, and I just sum up the number of ones in this key. So I have zeros and ones. So if I sum them up, then the sum I store in this HW, which is called the Hamming weight of the secret key. And this Hamming weight will tell me how many number of ones are in the key, in the secret key. And now an interesting application would be where this is used is that the question, which is to measure the side channel leakage in information flow. And what would be an intuition of a leaking side channel attack is that you can formulate it, is the Hamming weight kind of leaking? And in order to formalize this question, how you can do it, you take the same problem, or the same software problem, once again. Let me just show it. So you take 2 copies of the same problem. You can do it for finitely many copies as well, but let me just take 2 copies of the same problem. You introduce a bit of noise in your problem, and you want to ensure that no matter how this noise is introduced, the output or the value of this Hamming weight is the same in both of the problems. So let me visualize what I mean by noise. Okay, so assume that on the left-hand side, the red program, it takes as input this input array here, and the blue program takes a very similar array, except that it permutes 2 elements, so it swaps 2 elements. However, what you want to show that with this very small noise, you're not leaking. That is your Hamming weight computed on the red array, and the Hamming weight computed on the blue array remains the same. That is, the number of ones in your secret key remains the same, even if you swap 2 elements between each other. And this is what can be formulated in so-called hyperproperties. It's hyperproperties because you reason about not just about one program, but about sequences of multiple programs. So in this case, about 2 programs. And actually, it's in this case, the property would, so you can ensure that the Hamming weight computed on the red array, over the red array equals the Hamming weight computed over the blue array, because you only swap 2 elements, but the sum of the ones will remain unchanged by that. So while it's quite easy, let's say, to see that this is true, proving it will not be that easy. The issue is, because in order to prove that the red Hamming weight equals to the blue Hamming weight, so the 2 programs compute the same value, you have to first do a proof by induction over the bitwise equal, over the pairwise equal elements of both arrays. Then you just do a commutativity analysis, so pretty much commutativity of plus. Okay, if you add up V with W, you get the same result if you add W by V. It doesn't matter in which order you add them up. So you use a theory-specific reasoning using plus, commutativity property of plus, in order to make sure that the sum is preserved. And then you do once more proof by induction on the remaining part of the 2 arrays where they are pairwise equal, or element-wise equal, sorry. And these are the things that actually automated reasoners are not good at, because they use induction. So this kind of proof, we need to use induction, and induction is not a first order property. So automating proofs which are not even expressible in first order logic, it's quite hard. It requires a bit of creativity. Then you need to reason about theory-specific axioms such as commutativity. And now you might think, if you say that V plus W equals W plus V, you can take this infinitely many times and you will just prove the same property over and over again. You can apply infinitely many times the commutativity axioms, but you only need once. So while this is all great, actually, it's challenging. So if it works, and we actually showed in our paper, which I skipped now over, we have an automated reasoning approach for verifying so-called relational properties, that is hyperproperties. We show that actually, to some extent, we can automate such proofs. And let me just tell you, before I give you what is behind, let me tell you the results. So it turned out that by doing tailored changes in existing automated reasoners, we can actually push induction or prove inductive properties fully automatically, do theory-specific reasoning, again, fully automatically, and do all this in combinations. Vampire is our own theory improver, and we use with different kind of encodings, but the point is, I'm not going to enter the encodings, but the point of this table, what is showing, so the check marks are on which cases we managed to prove compared to other solvers such as CVC4 and Z3. And with very simple, well, very initial changes in our own automated reasoner, we actually managed to prove 11 problems that were actually deemed to be secure before, and now we just show that the analysis was not actually secure. So with this, what I wanted to exemplify with this example, so automated reasoning is great. It can do many things, but new emerging paradigms, programming paradigms, bring new emerging challenges for automated reasoning. And one challenge is how you express software properties in first-order logic, because automated reasoners use some formalization in logic. How you reason about first-order theories of data structures, such as, for instance, natural numbers, arrays, integers, and so on. And how you actually automate induction, how you do automated proofs where induction is needed. And these are the three reasoning challenges that are coming nowadays, and there are many other ones, but these are the three reasoning challenges that we are currently working upon. And in order to try to tell you how difficult or how fragile the landscape of automated reasoning is, let me tell you, okay, so what kind of automated reasoners can you use? So what is kind of the state of the art in automated reasoning? And automated reasoners, they are software programs or they're computer programs that take an input. And this input is formalized in some logic. So if you remember the very beginning, the first task of automated reasoning is formalize a problem as a mathematical or logical statement. So your input is going to be a logical statement. And depending, if you use only Boolean logic, if you only use propositional formulas, then you're in the domain of so-called SAT solving. And very nice SAT solvers, examples of SAT solvers are the Minisat SAT solver and the Linglink SAT solver. And they already had an impact, quite a big impact in hardware verification, for example, at Intel. If you go beyond propositional formulas, so if you start using fragments of first-order logic, but you also use theory, such as integers, arrays, lists, and so on, then you're in the domain of so-called satisfiability modulo theory solvers, which are the SMT solvers. Prominent examples of them are CVC4, nowadays CVC5, and Z3, and they have been used and are used at Microsoft and Amazon, for example. Now, on the other side, the nice thing about SAT and SMT solvers, because their input is kind of restricted, that is, they are only allowing propositional formulas or quantifier-free formulas over some theories, they are in the so-called decidable fragments of logic. That is, they can always, in principle, in theory, they can always prove validity of their input. On the other side of the story, they are so-called first-order theory improvers, where they allowed first-order logic with equality, potentially even with some theories, and therefore, because they have more expressivity in their input language, they are not decidable, or they are only semi-decidable. So they can prove validity, but cannot establish satisfiability. And prominent examples of theory improvers are, for instance, our own theory improver Vampire, or the E-theory improver, and again, we are used at Intel or Amazon. You can even go beyond first-order logic. For example, if you really want to express induction, you will need to go beyond first-order logic. For instance, you need to use second-order logic or higher-order logic. And then there are the so-called proof assistants, which are interactive theory improvers that require a bit of user guidance in the process of proving. And prominent examples of proof assistants are Isabelle, Koch, and again, they are used Intel, Apple, and other companies. So what I try to visualize in this slide is that there are many automated reasoners there. I only gave you here a few examples of some solvers, but they are very restricted to particular inputs. Such solvers are good for solving satisfiability of propositional formulas. SMT solvers are good at solving satisfiability of quantifying-free formulas with some theories. Theory improvers are good at proving, so establishing validity, not just satisfiability, but validity of first order formulas. And proof assistants actually require a bit of interaction, but therefore they use a very expressive logic. And depending where your application for software correctness, security, privacy, and so on lies, you need to choose which solver you are going for. What we are doing in my group, we are focusing on first order logic and try to extend the support of automated first order theory improvers, in particular of the vampire theory improver, in order to allow reasoning with induction, reasoning with theories, and also reasoning with software programs. So what is an automated theory improver, such as vampire or E? It's automated because once you press the button, you cannot interact with the theory improver. So but what I mean by you press the button, once you start running your theory improver, you press the button that the theory improver should run, and then you cannot influence anymore the process how the theory improver is behaving, unless you stop the execution of the theory improver. Our theory improver, if you're interested, you can go and download it. It's completely automatic. Once you start the proof attempt, you can only interrupt it by terminating the process of the theory improver of running. And there are championships in first of the theory improving. Actually, there are championships in automated reasoning, and Vampire is quite good in winning the main divisions in first of the theory improving. The nice thing about Vampire, so this is goes also in the direction of explainability or certification. Assume that you have a problem in first order logic, use Vampire, and Vampire gives you the answer, it's correct. Well, you also want to know why is it correct. So therefore, Vampire, what also produces, it produces relatively detailed proofs. So if you look at this proof, you can reconstruct the steps how Vampire actually proved your problem. We try to also, well, here I put it competes, but we try to bridge the gap between SMT and first order theory improving. So we also try to support not just first order logic with equality, but first order logic with equality and the theory of various data structures. In normal operation-based operation, it's so-called saturation-based, and I will show you in a minute what it means to be a saturation-based theory improver. But before that, just like any other automated reasoner, Vampire works the best when you use it in its portfolio mode. That is, you use it in combination with many different options of Vampire. And it supports many extra features, in particular for proving, for instance, system security. So what does it mean to be? So how is actually first the theory improver behaves? It's saturation-based, what I told you. But what does it mean? So how you give the first the theory improver an input problem, mathematical statement, and how the first the theory improver or an SMT solver usually behaves. It's very similar how a mathematician behaves. One of the most favorite proofs of a mathematician, and I'm also a mathematician, that we usually prove statements by contradiction. So what we do also in first theory improving, we say it's proved by refutation, but it corresponds proof by contradiction. So if I give you we are given an input problem with assumptions F1 up to Fn, from which we want to prove the conjecture G. So how we do it? This is our input. So internally, during pre-processing, the automated reasoner, we first negate the conjecture and establish the unsatisfiability of F1, Fn, and negation of G. So instead of proving G, we prove unsatisfiability of negation of G, and we call this process the refute G. So we prove unsatisfiability of the negation of it. And this is how it does. So I try to explain what is a saturation-based algorithm. And while it might be that the saturation, the notion of or the concept of saturation might be new to many of us, Actually, the concept of saturation is used in many different areas. It's a completion algorithm. So how it goes initially, so the theory improver has an input and it has its search space. It has its memory where it can derive many new statements from in order to prove its input. So initially, the input problem is the only problem which is stored in its search space. Now, this input problem can have many different problems. So you just pick your given formula. Initially, it's your input formula. So you just pick it. And you check whether can it be combined by some other candidate formulas which lie also in your search space, for instance, by some axioms. So if you can combine that, so if you can use the given formula with the candidate formula and derive a new formula, these new formulas are called the children of your given formula. But these children are not yet in your search space. So these are generated during proof search. So you add these children to your search space and your search space therefore grows. And you process this further. Again, you pick a formula, check against which other formulas can it be combined, derive new formulas, so-called children, put them back in your search space, and your search space is going to grow. So what we try here, we try to saturate our search space. We try to derive all logical consequences that exist from our input set of formulas. Except the point is that you might hit the memory of your search space. Well, in theory, this search space can grow a lot. In practice, you hit the memory of your automated reasoner. So the automated reasoner will terminate because it has no further resources. So in practice, there are three possible scenarios for an automated reasoner. At some moment, a proof is found. A proof is found, it means since we are proving the contradiction, it means whenever we derive the false formula, we found the proof. We proved unsatisfiability of the input. So in that case, the input is valid. In principle, you can also say that saturation, so this process which I showed you here, it can go, it in theory can run forever if you have an endless memory. So saturation can terminate without ever finding a proof. If you can measure what it means that without ever finding a proof, then this case, the second case, corresponds to the scenario that your input is satisfiable. And then the third case is, you just run out of resources without ever actually finding a proof. And then in that case, you will just report unknown. And that's the challenge, okay? Automated reasoning, it looks great, sounds great, it finds you proof if you're lucky. In most of the cases, we are either in 2 or 3. And the challenge of automated, so when we are having a proof, we don't care which proof we have. The first proof comes, the first one we take. And we terminate whenever we found the proof. We don't compare which proof is better. Once we found the proof, we terminate. However, it can actually be that proofs are not found because they're automated. So in this process, you see, there are quite many. I picked this formula, but I could also pick some formula in a different place. And I could combine this formula by some other candidate formula. So there are too many possibilities what an automated reasoner can do. So what we are having is that one challenge is, okay, how can we actually solve the unknown? But the reason where we actually terminate the process without knowing why, just we ran out of resources. And even in the second case, can we actually improve the performance? It might be that a proof is found in 20 seconds, but if you don't have 20 seconds, can you actually find the proof in 1 second as well? So we have to optimize the theory improver to be as fast as possible because it's usually integrated in a bigger process of software development. So the more time the theory improver or the automated reasoner takes, the more time the entire process of software development will take. And just to show you how, and this is actually what we work. I try to address these two challenges in automated reasoning. How do we solve the unknown? So how can we prove problems that were not provable before? And how we actually improve the performance of the theory improver to be as fast as possible. And for that, I just show you an example. It's quite an abstract example, but intuitively what it does, I want to prove that every non-empty set of natural valued array elements has a greatest lower bound. And now I'm going to just run Vampire. So what I wanted to show is actually running an automated theory improver is very easy. You just execute the command line option. And I'm running this Vampire with some options with a time limit of 20 seconds. And I'm just starting the run. And this is now actually how the Vampire theory improver internally behaves. I gave it 20 seconds to prove a problem. And eventually, hopefully it will stop. And actually it stopped and says, okay, it found the proof, because the refutation is the reason to found the proof in 8 seconds, almost 9 seconds, and generated 189 or 150,000 formulas within this number of seconds. Now I give you, okay, now you only have 8 seconds. You don't have any more 20 seconds. Do it better. And interestingly, still found the proof. Of course, now only less number of formulas, only in 3 seconds. And another example would be, okay, well, now only give you, let's say, 3 seconds rather than 8 seconds. And it still found the proof with a much smaller search space in much smaller time. And maybe just let's do like, can it find a proof in 1 second? And actually it can find a proof in 1 second. And the search space is much smaller. So initially I gave a prover to prove a problem in 20 seconds. And then the prover behaved very similar how usually we humans or even students would behave. I mean, students are also humans, but especially students doing the exam would behave. When they are, or let's just take researchers. When I as a researcher have a deadline, and I know that my deadline is in 2 months, I do many, many things in these 2 months. And this is what also the theory improver had. It had 20 seconds, so it did many, many things, and it generated initially a proof with 150,000 formulas. Now, if I would know that my deadline is tomorrow or it's now, I will be very goal focused, okay? If I know that I only have 2 minutes or 1 second to solve a problem, then I'm not going to store formulas that take me too much time to store. And that's exactly what the theory improver did here as well. I only gave 1 second time limit, and therefore it was impossible to store big formulas. And therefore found a proof, a different proof, but in a much faster way. So what we are trying to do in automated reasoning is that, first challenge, try to prove problems that were not provable before. And even those problems that were provable before, try to improve the performance of the theory improver. Try to make it faster. Try to find a proof as fast as possible. And our recipe is that we really want to bring first the theory improving in the process of software development. So generate, let's say, code that is correct by design, or ensure software correctness, or ensure system security within software in the process of software development, and therefore the process has to be very fast. Our recipe, it's very similar that we have it already from the 70s. You know, you don't have a proof, or you have a proof which is not good enough, so you just try and try again, and eventually you're going to hit the golden proof, or you're going to hit the golden strategy. So with that, okay, so that's kind of my tutorial of what an automated theory improver, automated reasoner can do. And what, based on this methodology, or based on these challenges, if we try to do with an automated reasoner, the focus is how we actually express software semantics in the input language of a first-order theory improver, which is first-order logic. How can we actually reason efficiently with first-order theories of data structures, and how can we actually automate induction in first-order theory improving, knowing that induction is not a first-order property. And for that, we introduce a so-called new logic, which is called trace logic, which is actually a conservative extension of multi-sorted first-order logic, which allows you to encode software semantics or software properties completely in trace logic or in multi-sorted first-order logic without translating into pure first-order logic with equality. The advantage is that what trace logic does, that in trace logic, we take program variables, or we represent program variables as being functions of loop counters, or being functions of other variables. And let me just give you the recipe how we do it. So we start with an input loop. And this input loop is not a loop. It's not an input to a first-order theory improver. The first-order theory improver takes some logical fragment as an input, not a programming language. So we need to express the semantics of this loop into some first-order language. And I'm going to use now two colors in order to explain how trace logic works. So we are given an initial program, an initial loop, and the loop language is defined by all the symbols that the loop is using. So this is the first order language. This is the vocabulary of the first order language I'm going to use. And then at the end, I'm interested in deriving loop invariant, loop requirements, such as ensuring that the software is, or the loop is correct, or the loop is secure, and so on. In order to do that, what we do, we extend this loop language. We introduce a bit more reasoning power in order to allow us to express more interesting properties about the loop. And we extend it with extra symbols, such as loop counters, so that we can express properties, what is a valid property at a particular iteration or at an arbitrary iteration. We also use so-called array update predicates that tell you at which iteration, at which position, with which value the array was updated. And then in this extended first order language, we are going to generate some loop properties and then derive consequences of these loop properties in order to show the required loop requirement. Now I use here two colors, right? So initially I only start with green symbols and I'm only interested in proving green requirements. However, during reasoning, I introduce additional symbols, the red symbols, and I derive these consequences as being logical formulas using both red and green symbols. I have more expressivity if I can use two colors rather than just using one color. And that's trace logic. But trace logic is an extended multi-source first order language or a first order logic where you can express loop properties, characterize the semantics of your loop by doing static analysis or formalizing using static analysis to formalize loop updates and use so-called trace lemmas to mimic induction. And we derive consequences, logical consequences, using a saturation-based theorem prover. So that's exactly what a first-order theorem prover is good at. And so here's an example for our running example from the very beginning. So we have this loop where we actually partition the input array into only positive and only negative arrays, fragments of positive valued arrays and negative valued arrays. And I have some requirements. I assume that this is the precondition, and at the end, I want to assert this postcondition. So what in trace logic we would do, we introduce some extra symbols, such as the loop counter, some loop iteration predicate to express at which iteration I am at, or I'm considering it. I consider loop variables, so the green variable, loop variable, becomes a function of an iteration. And I have some so-called array update predicates that tell me that how is a particular array updated at which iteration I, which position P, and by which element X. And now in this extended language, I can do static analysis and other things over the loop semantics. And for instance, by just lightweight static analysis, you can generate such kind of properties. For instance, let's just look at the second property. The second property tells you that the current iteration, so it just relates the values of the updated array element A, updated numeric variable A. So you know that the small a is updated at every loop iteration, and hence, therefore, the value of A at the next iteration is strictly greater than the value of A at the previous iteration. And similar things, so we just apply lightweight static analysis, and we can generate all these properties in first order logic, but in this extended first order logic, which is trace logic. So I have two colors. I have the green and the red colors. And ultimately, the automated reasoner is going to take this and many other formulas, but this set of loop properties in trace logic and derives consequences in order to prove the green properties. And by deriving consequences, it will try to eliminate the red symbol. So try to derive consequences which only contains green symbols, and such a green symbol can be the invariant that I already showed at the beginning of the talk. So the point is that it might, so you can use automated reasoning in a tailored setting for program analysis by making sure that you express the loop semantics directly in the input language of the automated reasoner. And trace logic allows you to do that. It gives you this multi-sorted extension of first order logic with equality. It's a conservative extension, and you can really express the operational semantics or axiomatic semantics as you wish of the loop. There are a few changes that we had to do internally in the automated reasoner to prove correctness of loop properties, but those I will skip in the interest of time. And I'm just trying to give you the end result that it's actually working. And again, we can compare Vampire with some other SMT solvers or some other provers such as CVC4 and Z3. And depending on different kind of encoding, you get different kind of problems. So what I mean by different kind of encoding, for instance, you can use arrays as array theory, or you can use arrays just as being a functional theory. And actually, so it turned out that in quite many challenges where you have software correctness properties where alternations of quantifiers or quantified properties are needed, that actually the first theory improver outperforms existing SMT solutions by doing reasoning in trace logic. Now, how we do the reasoning in trace logic, we need to make sure that the first theory improver understands the theory of the respective data structure. And what kind of data structures we are considering. So algebraic data types or inductively defined data types or so-called term algebras, such as natural numbers, lists. They are quite common in programming, but they are quite a burden for an automated theory improver or a first theory improver because they have some axioms which are not finitely axiomatizable in first logic. And such an axiom is acyclicity of a term algebra. So how we circumvent this problem by introducing an additional predicate, a so-called subtle predicate that gives you a finite axiomatization. And thanks to this axiomatization, this very tailored axiomatization of the respective theory, we make sure that all saturation-based reasoning process for the first theory improver can be further used in the presence of term algebras. And again, if you compare against other SMT solvers, so this tailored axiomatization of the term algebra in saturation-based theory improving actually outperform other SMT solvers. And before there is a misunderstanding, I'm not trying to say that Vampire or the first theory improver is the best. It's not. SMT solvers, they are very good in their own problems, but I'm trying to say that some tailored changes in the first order theory improver when it comes to first order reasoning, that is that you have properties with first order quantifiers and some theory symbols, then actually first order theory improver can become much better. And similar tailored changes are needed. So depending which theory you are looking at, you need a tailored change in your automated reasoner. You can consider it's a burden, but it is as it is. There is no universal solution, as we know from Turing. So for different kind of first order theories of data structures, we need different changes of the respective automated reasoner. For instance, in the case of arrays, we need to support the polymorphic theory of arrays with extensionality. In case of integers and reals, one can just go for incomplete but sound axiomatization of integers and reals. In case of naturals, one might think, do I want to work as a natural number, such as a term algebra? Or do I want to encode natural number just as an integer, just as as an integer mathematical number? So depending how you encode your problem, we have different processes or different rules in automated reasoners. And then the best is to use automated reasoner in a portfolio-based mode, that is different options are combined. And if your problem uses both term algebras and arrays, you need both options. And with this, what we try to do, and from the first order world, we try to bridge the gap between what SMT solvers can do and what first order theory improvers can do. So we try to come up with these automated reasoning procedures tailored to particular first order theories that can work with both first order logic and also theory symbols. And finally, the last challenge is Lilly induction. And this is quite a recent challenge that we are trying to tackle in the last 1.5 or 2 years. And the problem is, so I'm not going to tell you how, in the interest of time, I'm not going to tell how we integrated induction in first order theory improving. But just to recall, induction is not a first order property, so we cannot express it in the first order language of an automated theory improver. But what we can do, we can use specific induction schematas and instantiate it during pre-processing so that the instances are first order inductive properties. And this is what we do in first order theory improving. We use structural induction, for instance, and then we instantiate structural induction with particular symbols from the input and generate this and use this induction instances to prove inductive properties. And interestingly, this relatively lightweight integration of induction in saturation-based theory improving worked quite well. And interesting, it even outperforms some inductive theory improvers such as ACL2 or Raimandra, or even generalization of SMT solvers with induction. So what I try to convey, and I hope I managed during this talk, is that automated reasoning is great. It can do many, many things, but it's, whenever you try to, when you ever have a new problem and you use your automated reasoner for a new problem, you have to adjust your automated reasoner for a fast and efficient solution for the new problem. And in particular, in the setting of program analysis, well, you need to ensure that you can express your software semantics in the input language of the automated reasoners. And for that, we propose trace logic. You need to come up with automated reasoning procedures for first the theories of data structures. And we have various automated reasoning procedures for various data structures. And you need to integrate induction in a light way in the saturation-based theory improving process of the automated reasoner. Yet, it doesn't mean that everything is solved. Actually, we just scratch the surface. And I do believe that automated reasoning will remain central in rigorous system engineering or in system development. To some extent, it's great that the role of automated reasoning in these areas is already growing. And I'm confident that it will be growing thanks to emerging applications of security, smart contract verification, cloud computing, and so on. There is one big challenge which I might have hit during the presentation, is that I understand quite well what Vampire or what our automated reasoner is doing. However, this automated reasoner is it's used by a large number of users who do not understand what an automated reasoner is, how is saturation performing, and even more, this user might have very elementary knowledge of logic. So it might be that the users of the automated reasoners already encode their problem into an input language which is not adequate for the automated reasoner. So therefore, I do believe that formal reasoning or formal automated reasoning cannot be handled by the engineers alone. It's too complex. It requires expertise from the domain experts as well. However, we alone cannot solve. So it requires an interaction. We might come up with too complicated solutions which solves many problems which in practice don't come up. And this is, I think, actually one very fascinating area of automated reasoning, is that you need experimental driven theoretical development of automated reasoning procedures. I do believe actually that automated reasoning with theories, in particular with theories of data structures, will remain the main challenge in ensuring system reliability, at least for the next 5-10 years, maybe even more. And working with big data, big theories is going to be a challenge that we are going to face in the next years, and we are looking forward to that. With that, I would like to conclude, and I'm happy to take questions if there are any.
Okay, Laura, thank you very much for a talk. Gordana has a question. Gordana, get and turn on your microphone and you can go first.
Oh, it was actually not a question. It was just a plot. I was appreciating the talk. That was all.
Thank you very much.
Okay, an applause. Okay, we're going to save the applause for the end, though. Other questions from the audience. So one question that I have is, when you do a syntactical analysis of some algorithm, right? As you showed, you take the syntax and you try and derive the semantics from that. The syntax are pretty clear in the examples, or reasonably clear. Can I fool a verification system by using a not so clear syntax? I'm not sure why I'd want to do this, but could I? Yes. Is it how to what degree is the clarity of the syntax and the programming style, the regularity of the programming style, essential for the verifier to work?
Yeah, it's actually very, so there are two multiple aspects of this question. But for instance, you can introduce a lot of randomness in your problem. It will affect a lot the performance of the verifier. You might have actually the same problem, right? Let's say you have let's say a big number of formulas, but let's just take 5 formulas, okay, in the semantics, but you just shuffle around them. And it will influence the performance of the verifier. Although it's the same problem, but the selection of the given clause or the selection of different formulas might vary on that, especially when you have a big number of formulas. The other thing is that definitely the program the syntax actually influence also the semantics. So in various ways. So for instance, you can one can actually do SSA transformations or all kind of optimizations from compilers in order to have the most succinct or the most loop-free language or most if-then-else-free language. This will not be necessarily the best transformation for a theory improver. Actually, for instance, in the theory improvers, the automated reasoners, you have tailored support for if-then-else and Latin expressions. And it's much better if we make the pre-processing rather than the user. So it's very sensitive.
Okay, but in practice, when do you get to see the code? If you look at some of your partners, do you get to see it, the optimized code that a compiler tosses out, or do you get to see the source code before it gets to the compiler?
I believe we get, so it's not just me, I think so it's in the academic community, we have these benchmark repositories, and we get, well, it's not really from the partners, it's some copyright not protected code, and it's the source code.
Okay.
And then this is how you can create different kind of challenges for different solvers. Introduce a bit of randomization, different kind of encodings, give different kind of problems.
But if the syntax and if clarity is important, then that seems to me that what you really want in the future is to embed the proving as part of almost a compilation step, to have a compiler that doesn't only do syntax analysis, but also does a semantic analysis based on the formal on formal proofs at the earliest possible moment rather than the latest possible. Is that true? And if that is true, are there moves to develop formal compilers?
Oh, so I think that, yeah, so I don't work really on the formal compiler development, but there's actually substantial work on that.
Okay.
Even by colleagues at Chalmers or also colleagues in France, in RIA. But so I think there has to be a trade of how early and how late you do the theory improve. If you do it too early, so this technology is actually quite expensive. So if you do it too often, it will not pay off. But if you do it too late, when all the optimizations are done, then it will probably not bring the right effect. So it should be in between. And this is actually where I think it's more what's important, to have this interaction between the developer, the software developer, and the developer of the verifier that interacts, at which point it calls the theory improver or the automated reasoner.
Okay.
So actually, I think that some compiler optimization techniques should be applied and should be removed before you just apply the theory improver.
Okay. These the examples you showed are pretty deterministic. Are they? They're also invariant in the sense that you're always going to get the same results every time you run the code. The work that I do is largely in interactive systems where there's a lot less predictability of the kind of inputs you're going to be getting, certainly if time plays a role. What's the role of time in this work? Is there a role? Is temporal logic important? Are the kind of problems you look at, are they deterministic and fairly semantically static?
So I think that again too, so whether they're static, you might get the same result in terms of validity or satisfiability of the formula, but you might get different proofs depending how much is your, and this is what I try to show, that you get different, depending on how many resources you have, you might get different proofs, and actually you do get different proofs. Now, whether with respect to temporal logic, yes, you can actually use modalities, and also you can have extensions of I mean, there are extensions specifically used by model checking tools that use event-tree reasoning or until operators, but ultimately at the end, they will translate the problem currently to an SMT or an automated reasoner.
Okay. Okay. Great. And my last question is, when I first looked at this, people always talked about a space-time trade-off. In a lot of things, space is less of a concern because we've got a whole lot of space, right? Memory is relatively large. And we've also got a whole lot of time because machines have gotten very, very much faster in the last decades. Is there still a space-time trade-off? Or is, if it's important, do people have the time they need to do the kind of verification that makes most sense for a problem?
Oh, I think even if we would have endless space and we would have endless time, there will be still problems which machine will not be able, at least current machines will not be able to solve. It will just replace the mathematics. Sometimes you need this intuition. You need to have the educated guess how you made the right abstraction. And this is currently we don't have.
Okay.
I don't think this, unless, so there are even theoretical results showing that this cannot be, that you just solve every problem. For every problem you find an algorithm.
Right, right. Although I assume people are selective in the problems that they apply to this so that they'd have a hope of actually getting a result. So excellent. Well, let's see, are there any questions left? And let's see, Alexander has a question. So Alexander, turn on your camera if you can, if you want, and in any case, turn on your microphone. And
Hello.
go ahead. Hi, welcome.
Yeah, my question was, is there any work on the certifying correctness for the automatic reasoners themselves? So reasoning on the reasoner's code?
Yes, there is. So it's actually very hard, but there are approaches for it. There is a deductive framework. There is also the sledgehammer framework. There's also quite the old framework from proof carrying code. That you want to certify that both the prover and also its output is correct. And it's actually quite a hard task because the proofs that the prover produces is very compact, and some of our steps are from 10 steps, we just reduce it to 1 in the proof because proof takes place as well. Okay. So there is work, and I think the most sensible way there is that you try to identify a core logic for which you certify, and everything on top has to be additionally certified. Okay.
But is this work mostly falling into the automated kind of style or interactive, would you say? It's
in between. So it has also interaction, but then there's some interaction at one point, but it tries to automate as much as possible.
Okay, I see.
So I believe the sledgehammer, I think sledgehammer has both interaction and also automation.
Okay. So it's like Isabel based. Okay, thank you.
Okay, and then 2 questions in the chat, or I don't know if you can see the chat or if you want to open the chat from Timor. The first is, do you actually prove that the loop invariant generated by the approach, right? So the first,
we don't. That would be actually. I'm not even sure we can do that, but we only prove that the invariant that we generate it's strong enough to prove the given assertion. So we do it property driven. Depending what we want to prove, we generate the right invariant.
Okay, and then we have a second question, or is that maybe more of if you have a chance to compare your technique with contemporary loop invariant generators?
So we didn't really compare to DICON because DICON also had this likely invariant aspect. So, but we compared not exactly this work, but a fragment of this work on nonlinear invariant generation. So for instance, I showed this example for the Fibonacci number, where you have this polynomial invariance, and we compare to other approaches. There are examples where we are actually much better, and those are the ones where you need algebraic numbers, so you need full computer algebraic support. But there are approaches, quite many approaches, they are better in the sense that they can handle a much larger class of programs. So for instance, we will only be restricted to loops with if then else statements, but we cannot have arbitrary nestedness in the loops. And this is something where template-based generation, invariant generation approaches would be much better at.
Okay, And now we have a last question that goes to Elisabetta. And if you can turn on your mic and your camera.
Hi.
There we are.
So my question, first of all, in the very last part, when you were answering to the questions, I was busy answering the phone. So maybe you have already covered this point. I do apologize if this is the case. But my question was really related to one of the last points you highlighted in the conclusion, where you said that you need engineers and you need domain experts. What I did not understand is whether by domain experts you mean experts of the specific theorem proving techniques, or experts of the domain intended as experts of the application.
I think you need both, because depending on the application. So for instance, we would need the domain experts in terms of the application to understand what is their problem, because for instance, the domain expert in the terms of the application might encode a problem into an unnecessarily complicated logic. And therefore you would need, let's say, the logician or the automated reasoning expert to tell you what is the best encoding. Or another example could be if you have an encoding which is only in Boolean logic or some extension of decidable fragment of first order logic, there is no need to use a first order theorem prover. This is not the strength of the first order theorem prover. And similarly, if you have a first order logic encoding, there is no need to use a SAT solver because it's not the expertise. So I think it's really the interaction of the both expertise. You need the encoding or the understanding what is really the application, and then try to come up with the right reasoning engine. And it needs to have a bilateral.
So in the end, you need an expert, a logician, you need the application expert, and maybe the engineer who is developing the system, or this could be just this is not relevant given that the theorem prover or the tool that you use can be automated.
I think the engineering is actually very relevant, because you can automate some things, but the naive automation will not bring you the fastest solution. So I think it's really a combination of quite many functional, let's say, characteristics. And this is why this technology, I'm aware, is not cheap. It's quite expensive, and therefore it should be used carefully. So as I said before, I don't envision to use a theorem prover on the first step of software development, but there will be steps where you cannot get out without having a certification.
Thank you.
Okay, an interesting problem in logic is the completion problem, but we're going to solve that right now by saying this ends our seminar. Thank you very much for joining us. Thank you very much to Laura for an invigorating talk. And it certainly leaves me with the impression is there's a lot of work left to be done. So if you've got bright students, this is one of the places to send them to, because there's a lot of fruit. I don't know how low hanging it is, but there's probably a lot of fruit out there. Laura, thank you very much.
Thank you.
Have a good summer. As I mentioned, this is the last of our research seminars for this season, but starting next week, we have another series of seminars, and check on the Informatics Europe site for this and future seminars in this series. Thanks to everybody. Have a good summer, and we'll see you in the seminars next year.